It is mucho hot outside. Whew. All right, let's get rolling. We are into phase 2 out of the 3 phases that we have in the course. And our next phase begins with equilibrium. Most of this phase is going to be on acid-base chemistry. Lots and lots on acid-base chemistry. This, however, is not acid-base chemistry. We're preparing for it. We have to do the topic of the day, the word of the day. Remember the word of the day in the very first video we had of the course. It was intermolecular forces. Remember that? Then the word of the day was colligative properties. You remember that? Then the word of the day was reaction rates. And then I'll tell you the word of the day is equilibrium. Equilibrium. All right. Now I had mentioned equilibrium. I had mentioned that in a video, I think it might have been the first video, we were talking about equilibrium vapor pressure. So I have mentioned it, but let's go through it one more time because it's really important to understand. All right, now, I will give you an analogy. An analogy. I like to use my Walmart analogy. Well, I don't know what time Walmart opens, but let's say it opens up at 8 o'clock in the morning. Okay, so you're outside of Walmart, you know, they got a really good deal. Maybe it's like Black Friday, and there's all these people in a day after Thanksgiving where everybody's freaking out. You gotta get that one TV that's on, it's like only for $100. Everybody runs in and tramples each other and has mass hysteria. Okay, raining cats and dogs. It's just a mess. It's a mess. It's a mess. But let's say there's a whole bunch of people outside waiting to get in to Walmart. Doors open. Okay, my analogy here is the reaction hasn't begun yet. As soon as we open the doors of Walmart, the reaction starts. So prior to going into Walmart, we have the reactants outside waiting to do their thing and start reacting and going in. Okay, you getting my analogy here? So people are outside of Walmart, you open the doors and boom, everybody's going into Walmart. There might be one person coming out. That might be one of those disgruntled employees saying, I am out of here, I'm not dealing with this crowd. And they're going on the way out, okay? But not very likely anybody's coming out when those doors open. So everybody's going into Walmart, okay? Now, let's say let's fast forward to noon. Okay? Several hours later, people are going into Walmart, people are going out of Walmart. Basically, if you watch Walmart for 15 minutes, you will see 8 people go in, and on average, 8 people go out. And so everyone that goes in, you have someone else coming out. That's equilibrium. When Walmart is getting near closing, attention shoppers, you must leave the store. We need to go home, and you need to go home, so get out of here. And they'll say, 5 minutes left. At that point, no customers are going into Walmart anymore. Everybody's coming out of Walmart. Not equilibrium. Okay, when a Walmart opens in the morning, everybody's going in, nobody's coming out. Not equilibrium. Equilibrium. In between, when for every person that goes in, you have another person coming out, and that's on average what's going to happen. That's equilibrium. So what is equilibrium? Okay, now here's the other thing too. The thing about equilibrium is everybody thinks, oh, so let's apply it to chemistry now. So if I have a chemical reaction going on, and I have chemical A and chemical B forming chemical AB. Maybe it's a synthesis reaction, okay? Up to this point, all the arrows that we've done in your chemistry and our chemistry have been in one direction. Arrows in one direction, one direction. I'm so upset they broke up. They were so hot. I love them. They were awesome. A band? No, I didn't really. Just saying that. But I didn't know they were around, so at least I got that going for me. At least I knew that they were a band. All right, so everything's going in one direction. But that usually is not what happens. That is highly irregular. And unless we have what's called a strong acid or a strong base reaction in this unit, you don't have the arrow going only to the right. There's an arrow going back. And this is quite common with chemical reactions. The reactants form product, but the product can reform the reactants. That's a two-direction arrow. Now, I typically will write it just as an arrow with 2 arrowheads. Got it? All right. That is two-directional. Now, in this case, we always write the reactants on the left and the products on the right. Now, some of you might be saying, well, wait a minute. What if the reaction goes backwards, goes in this direction, would that be the reactants and these the products? Yes and no. Yes, your logic is sound, but however, in order to keep everything in agreement in the chemical world, We always say the reactants are the things on the left and the products are the things on the right. If you want to emphasize the other way around, you need to reverse this reaction and put AB over here. So the reactants are always the things on the left. The products are always things on the right. Even with a two-way street here, a reaction going in both directions. Okay, now here's the thing about equilibrium. Equilibrium, if we were first to take chemical A and chemical B, and we haven't mixed them yet, okay? We take them and we got a little, like our witch's cauldron. Yes, matey. That was kind of a combination of a witch and a pirate. It's one of those witchy pirates, right? And you take your chemicals A and B and you dump them in. Okay, now they're going to start to react. Remember Walmart when it first opened in the morning? What's going to happen? You're only going to get these forming the product because this product hasn't been made yet. It hasn't had a chance to leave the store. Are you getting my analogy? Now, after a while, when we make enough of AB, then some of the AB will start to go back in this direction. And once we have as many ABs forming A, many ABs forming AB, and as many ABs forming A and B, then we have equilibrium. All right? Okay, as many in the store as out of the store. As many making product as these products reversing and then remaking the reactants. When we have equal amounts going both ways, we have equilibrium. But here's the misnomer. Here's the thing, not the misnomer, the misconception is what I meant to say. Misconception is this, that at equilibrium, you have equal amounts of reactant and product. At equilibrium, you have equal amounts of reactant and product. Wrong. Wrong. I mean, it's possible, but highly unlikely. Let me go back to my Walmart analogy. Okay, let's say that you go to the Walmart. Where's one near Manchester? There's one in Hooksett. All right, there's one up there in Hooksett, just before you get into Manchester on the way to MCC, coming off of exit 10, I think it is, off of 93. Well, Walmart's in Hooksett, right? That means that there are people inside of Walmart and outside of Walmart in Hooksett. Well, it's noon at the store in Walmart. You have just as many people going into Walmart as coming out of Walmart going into Hooksett. Just because you have equal amounts going in and out of the store does not mean you have equal amounts in the store and out of the store. And that's crazy. Hooksett's bigger than what you're going to hold inside the Walmart in Hooksett. So there is clearly a lot more people outside the store. I mean, in the world, you can go to that extreme. There's a lot more people in the world than there are in that one Walmart in Hooksett. So just because you have equal amounts going in as coming out does not mean you have equal amounts out of the store and in the store. Important. Just because we have equal amounts of product and equal amounts of reactant going back and forth for one of these, one of those, two of those, two of those. That doesn't mean you have equal amounts of these and these. You could have a crap ton more of these than these, or you could have a crap ton more of these than these. Okay? So, remember, here's the important thing about equilibrium. Two things. Two things. Here we go. Two things. Equilibrium means you have as much reactant as you have making product. So for every 1 mole of this that's made, there would be 1 mole of this breaking down and reforming this. 1 mole for 1 mole or 2 moles for 2 moles. But that doesn't mean you have equal amounts. You could have 50 moles of this and 1 mole or 2 moles of something of this. Okay? But you don't necessarily have equal amounts of them. You just have an equal exchange of them. I know I've repeated it like 3 times, but that means it's like muy importante. Okay, I'm looking at the sheet here. Here's our sheet of topics that we have for today. It's kind of spread out. Okay, you can see that. And we're doing equilibrium, and it says chemical and physical. Well, I mean, equilibrium can exist with physical equilibrium, and my example of Walmart was physical equilibrium. Okay, and people aren't chemically reacting with each other when they go in and out. They'd be kind of weird, right? So that would be an example of physical equilibrium. Of course, I'm using a chemical equilibrium example up here, and we'll use many of those today in the class and the problems. I mean, one more example of physical equilibrium is you have an ice bath. If you had an ice bath, that means ice and water at 0 degrees, like your freezer's at 0, you would have just as much water melting as freezing, and that would be another example of physical equilibrium. For every molecule that melts, you get one that freezes. So, well, actually, technically, you couldn't get one water, I can't even talk, I'm so excited. One water molecule freezing, you would need 6 of them, but you get the point. Okay, so now let's talk about what's called an equilibrium constant. On your sheet, you will see equilibrium constant, and it says Kc or Kp. There are actually many equilibrium constants. Equilibrium constant is the letter K. K? K. It's funny. Which it has been so far. We've been using K. Now I'm using big K. Equilibrium constant is big K as opposed to little k. So little k, I've been writing my cursive little k's because my little cursive, non-cursive little k's look at my big k's. It's really confusing. So big K means equilibrium constant, but there are many different equilibrium constants. There's Kc and the Sunshine Band. Shake, shake, shake. Shake, shake, shake. Shake your booty. Boop, boop, shake your booty. I'm shaking my booty right now, but you do not want to see that. I'm sure you do not. So I will move on, okay? Thank you. Kc. There's Kp. I used to do KP when I was in Boy Scouts, Kitchen Patrol. You're on KP, Gundram. Aww. That means clean up the kitchen. That's not what it means in chemistry, though. We have Ka. We have Kb. We're going to find we have KSP. KSP, I had some of that chicken. It was really good. KSP, Kentucky Fried. No, wait a minute. It's KFC. Now, I'm so confused. Okay, so these are different equilibrium constants for different things that happen in chemistry. This refers, as we're going to find out very soon, to concentrations in aqueous solutions. Concentrations in aqueous solutions. This is pressure. This means gases. This one is acids, bases, and this one is SP. We'll find out that solubility product constant, which means salts in solution, specifically, that don't dissolve. So all the way. So non-soluble salts is we're going to find that. Okay, so you don't need to know these right now. Don't need these any right now. We'll get to those soon enough. But we need to know these like right now. Okay, but I'm going to cut this video at this point, so that way we have a relatively short introductory video, and we'll see you very soon.